Good morning, everyone. I am Daniela Zeppilli, the head of the Deep Sea Lab at IFREMER in France, and I would like to discuss with you the needs for microscopic observation of deep sea sedimentary fauna. Before we move to the deep, let me just spend a few seconds considering what we can learn from another microscopic compartment, the plankton. I was really inspired by the Tara project, which made a revolution in our comprehension of planktonic biodiversity, using several techniques such as omics as well as imaging. In particular, I was impressed by this work, which used 3D fluorescence imaging and classification tool for high throughput analysis of microbial eukaryotes. And here you can see a 3D animation of a diatom, which illustrates the synergy between staining strategy and optical selection microscopy. In green cellular membranes, in blue DNA used to identify the nucleus, in red chlorophyll, and in gray a counter stain for visualizing the specimen surface. Back to the deep sea, so why look to microscopic organisms? Because more we go deep, more we can experience a reduction of animal size, except for chemosynthetic oasis, that is usually associated to an increase of species diversity. If you take a sediment core in an abyssal plain, you can have something like thousands of nematodes, dozens of copepods, and a few other specimens coming from other taxa. Some characteristic of meiofauna related to imaging is first that they are very tiny. We consider meiofauna all the organisms passing to a 1 mm sieve and retained into 32 micrometer sieve. They live in the sediments, a very dirty environment, and they are 3D entities. This means that taxonomical and functional information are in different layers. Here an example of a Desmodora nematode where you can see on the left the upper focus with taxonomical information on the cuticles, and on the right the internal focus with the functional information such as the presence of tooth, an indication of its trophic habit. As I just say, meiofauna live in sediment. Here what you can see, if you just take a spoon of sediment and you look at it at the stereomicroscope, grain of sand and sediment everywhere and some camouflaged organism, here an ostracod and a nematode. And again, some pic from confocal where you can see particles everywhere, and just a nematode. Second important thing is meiofauna organisms are 3D entities. So if you choose 2D imaging, you will need several pics, as I showed before. So here an example of a nematode, Odontostoma species that you can see in 2D. So this nematode has a very complex cephalic capsula that is not easy to describe in 2D. And the same nematode observed at the confocal in 3D, you can see that you have all the layers of the animal with a very high definition of the tails at the same time. And here, again, another 3D acquisition of the same specimen where you can see this complex cephalic capsula and very high quality detail. Another interesting thing we can do is also to associate normal imaging to genetic probes. Here an example of a nematode where we discover symbiotic bacterial communities on the cuticle. So on the left you can see some detail of the tail where we observed different bacteria shapes. And what we did is use fluorescence in situ hybridization on the right, where you can see in blue the nuclei of nematodes, in green gamma proteobacteria, and red epsilon proteobacteria. And using axiozoom, we observed that these nematodes host different bacteria involved in different metabolic processes to better perform in an extreme environment. We can resume here some kind of microscope that we can use for meiofauna description, considering the resolution and the type of images we want, the speed of acquisition and the data size we get, and of course the price of the microscope. Starting from the optical bright field ones, They are quite fast, but they demand several peaks for specimen to have all layers, and the quality and the size of images really depend on the kind of microscope. The range of price is very large, and this makes the difference. The confocal ones are very high resolution 3D, but they are slow, with large data sites, and they are very expensive. Acute zoom have high 3D resolution. They are faster than the confocal, but they are still quite expensive. An example of the scanning electron microscope, the quality of images is very, very high, but only external and slow and again expensive. And there is a lot of development for microscopic camera in flow. We can find 2D and 3D, and the quality of images can be low to medium. They are very fast and less consuming in data sites. And again, we can have a very large range of prices. So, which is the right compromise? It really depends on what we want to do. For high resolution biodiversity studies, we need very clean samples or individual picked organisms, high resolution 3D images for feed open access depositories. This can be the basis for the development of automatic identification by artificial intelligence. While for environmental survey, we need dilution of sediment in flow, faster low, medium 2D, 3D images that can allow quick acquisition of several ecological information, such as abundance, biomass, and can be automatically identified by artificial intelligence at low taxonomical level. This combination of methods is something we are testing now in the ongoing Blue Revolution project, where we would like to automate the acquisition of images of sediment fauna for an automatic identification by artificial intelligence, proposing a combination of both methods and high-resolution imaging associated to genetic assignment for feeding depositories, and the faster low-resolution imaging associated with ADN metabarcoding for survey. We have a lot of challenges in this project, but we hope to propose a standardized method for ecological and biodiversity survey. And that's all. Thank you for your attention. I'm ready to reply to your question.